Yeah, and he was not blazing. He was in a. He was going pretty slow.
I thought he was going pretty quick, wasn't he?
No,
Maybe I'm misremembering
no,
it. That was a long time
no.
ago.
He was just cruising. I mean, he was just cruising, man.
It might have looked like referentially just relatively quickly.
I was like 10, so when was that? Like 1994,
Was he?
something like that. It was a while ago.
Yeah, it was a while ago. You know, he's a much older man now.
He just got out of prison, didn't he?
Yep.
For unrelated charges.
Yep.
This
Yep.
is like, you ever see that the judge when they busted him for robbing that convenience store? They're like, you dumb shit, you got away with murder, and you rob a convenience store. This is what gets you arrested.
Technically, it is. He could not convict you of murder.
He couldn't convict you with murder. He gets away. Oh jeez.
I'm a typical programmer. I cannot work in bright environments.
You haven't had Kardashian. What's his name? George Kardashian?
His name's Bob Kardashian, right? The
Robert
father?
Kardashian?
The
Yeah,
father,
lawyer.
yeah, but that's how the whole clan got famous.
Yeah.
Yeah.
Yep.
Not Kim, but the rest of them.
Yeah.
What's
Yeah.
Kim Kardashian famous for? For being famous?
Well, for trying to be famous. How about that?
Well, she is famous. We know her name.
Famous wannabe.
When you start up,
Can't
would
be
you
wanna be
mind
famous
briefly
and
going
recognized.
over the final lab question from the previous?
Absolutely. Yeah, we can do that.
Kind of the definition of fame.
I want nothing like that.
It's 3, 2, 1. It's 3, 2, 1.
Okay, I need to reset my display.
And 4 minutes ago, size 6543221.
What?
The time it was when 6:54.
Oh, okay,
on
I
March
see.
21st.
Okay, coincidence.
6543221.
Coincidence.
Highlander night. Oh, but no, I mean from like the medieval. He was like, because I know he's immortal, so he was born a Highlander.
All right, so we're gonna get started here.
Yeah, that's why I was corrected. I said Highlander.
I'm having a scratchy throat today, so my voice may not project as well today. So what we'll do today is because of a request, we'll go over some of the previous lab first, and then we'll start with what we want to do today. So that's good too. So the lab activity on Monday is this one, and let me just kind of go over each individual question, and so I will explain how I would answer those questions, and you guys can ask questions about that too. All right, so the first question says, the increment instruction increments the value of a register. Is that what we did on Monday? I think so, it's 19, so that should be it. But it does not affect the flags. This makes the instruction more useful because in many situations, the objective is just to increment the counter, but we do not want to change the flags. Yes? I believe so. Yep, it is being recorded. But it is important to preserve the flags from the previous compared instruction. Using the opcode table or the assembler, find out the binary opcode of the following instruction. Increment C, so we want to increment register C. Express your answer as an 8-bit binary number, which means I need 8 digits. Each one is a 0 or 1, without any space between the digits. So to answer this question, we basically just need to look at the opcode table. So let me go back to my drive and then go to cisp310. So up a little bit more. There we go. Go to shared, go to processor, and then go to the opcode table. And then we look up increment, INC. So Control F,
INC, and here we found it. Okay, so INC has an opcode of 1101 XXXX. So in this case, I put an extra space between the XX and the XX just to be clear that it is the same 2 bits repeated. Okay. So that means we are looking at so which 2 bits represent register C? 1 0 because it is 0 1 2 or ABC, so it's 1 0. So in this case, it's 1 0 that is repeating itself. So that means we have a bit overall bit pattern of 1 1 0 1 1 0 1 0. And that's the answer. Okay, 1 1 0 1 1 0 1 0. So let me go back to my lab activity here. 1 1 0 1 1 0 1 0. That's the answer. Are there any questions about this one? Nope. Okay. So I'm trying to include an instruction like a question like this, for each quiz, just so that we are kind of practicing how to assemble the opcodes and stuff like that. Because the more we practice, the more proficient we get in doing something like this. The jump immediate instruction has an immediate operand. When it executes, it changes the program counter to what the immediate operand specifies. Consider the following instruction: JMPI some label. When this instruction executes, the processor continues execution where some label is defined. This unconditional jump/branch instruction, is just a terminology thing. Some manufacturers, decide to call this a branch instruction, while other manufacturers, want to call this a jump instruction. Jump is a little bit more common. Branch is kind of less common, but they can be found as well. It's used to handle the case when a conditional branch does not branch. This is mostly because the TTP lacks conditional branch instruction that branch when the flag is cleared. Consider the following code. If execution continues at label L2, okay, most likely because of the JMPI L2 instruction, after the code, and assuming L1 and L2 are defined at different addresses, so that people cannot say, but what if they're the same? Then we end up at the same place and we cannot tell anything about the ordering between A and B. So I make sure that they are not at the same place. What can we conclude about registers A and B while it is at label L2? So the question now is, if we execute the program backwards, okay, it means that this JMPI instruction must have executed because we ended up at label L2 right after these instructions. But this won't execute if we did the conditional branch to L1. It would not have executed if the carry flag was a 1. So that means the carry flag must be a 0. So if the carry flag is a 0 after a compare instruction, which essentially is a subtraction, so that means the middle-end is not less than the subtrahend interpreted unsigned. Okay? So when you look at the answer, there's no such thing as not less than, but there's a greater than or equal to. So the answer is unsigned A is greater than or equal to unsigned B. The use of the unsigned as a typecast is to emphasize that we are interpreting the bit pattern of A and B as unsigned values. So that's why it could be typecast operator, just to emphasize that this is unsigned as opposed to signed. Are there any questions about this particular question? Good. Okay. All right. So let's move on. Click next. All right. So the next one is one of the most useful tools in Logisim. Okay. So this is about the logging part. And I'm just going to skip all the way to the end. Is that okay? Okay, so after the processor is loaded into Logisim in the selection tab of the log window, what is the fifth entry of the left column from the bottom? It's PC. Yep. So you just write down PC, and I emphasize that it is case sensitive. I hope nobody put in lowercase PC. Okay. And then this is the last question, which is the real part of the previous lab. Okay, all the other previous ones are pretty easy to do. So with this one, copy and paste the code and go ahead and run this code. And I want you to change the JXI instruction so that the no op instruction at label L2 executes as many times as possible. Okay, so there's an easy way to find the answer, and there's a long way to find the answer. It kind of depends on how you like to do things. So the question is, how often are we, or how many times? Okay, I should say how many times we execute this particular no op instruction at label L2. So now we have to kind of backtrack and say, okay, if we execute at label L2, what does it mean? All right, so we go back up. The instruction right before this one is an unconditional branch. So that means, we could not have come from this branch here. So the only way to get to label L2 has got to be this unconditional branch instruction. But this unconditional branch instruction could not have executed if the flag, whatever X is specifying, is 1. So that means the compare instruction must have cleared the flag in order to get to L2. In other words, an earlier question is helping you to answer this question. I even preserved the label L2. Does that make any sense? Did you guys link that? Did you guys realize that an earlier question is related to this one? No. Not at the time? Okay. So I buried the hint a little bit too deep. Yep. It really cannot do anything without ID or IDN as labels because the program is not even assembled.
No, but like the answer would change depending on the
Aha. Okay. So maybe and maybe not. Okay. So you look at the 5 flags, right? You got 5 flags to choose from. And the question here show you all the 5 options too, right? So there's C. Okay. Now C definitely depends on your student ID. Okay. If your student ID does not have 2 adjacent digits being the same, then JZI would give you the maximum. Because we want the Z flag to be clear. The Z flag being cleared means whatever you're comparing are different. And the rest of the program is really just A and B are 2 pointers. They're only off by 1 byte. In other words, I'm comparing the first digit with the second digit with the third digit, and so on, until we have compared basically all 7 digits. Okay? So that means that means JCI will give you the maximum count already if your student ID has no adjacent digits being the same. So in my case, it's not going to give me the maximum count because my ID is 0006887. So the first 0 and the second 0 will match, which means it's not going to go to L2. The second 0 and the third 0 will match, it's not going to go to L2. And then the 2 8s will also match, and that's not going to go to L2. So in my case, it will only go to the no op 3 times instead of up to 6 times. So JCI may work in many students' ID unless they have adjacent digits being the same. So how many of you have adjacent digits being the same? Okay, so JCI would not work in your cases. Okay. The next one is carry. So carry is basically saying A is, it means C is less than D. So in order not to branch, that means C has to be greater than or equal to D. So unless you have a very strange student ID, like 1, 2, 3, 4, 5, 6, 7, which means it is sorted in an increasing order, that's the only ID that will have 6 times going through the label L2 using JCI. So does anyone have a student ID like that, where the digits are sorted in increasing order? It's pretty rare, but it does occur occasionally. So none of you have that. So JCI would not work with any one of your ID, and neither would JSI. Because JSI is looking for the sign of the subtraction, and because your digits, okay, one digit from the student ID can only go from 0 to 9. Okay, so can you find a subtraction with that range of values that will go out of the range of a signed 8-bit number? What is the range of a signed 8-bit number? We talked about that. There's a general equation to figure that out.
226.
Okay.
Plus or minus 123.
128 to positive 127. So that equation is in one of the modules, okay? But you got the range right, okay? So negative 128 to 127. So is there a chance in a subtraction when each number is 0 to 9 that we will exceed the range of negative 128 on one side or 127 on the other side? Nope. Okay. So that means the sign, is going to be the same as the borrow in this case because of the small range of values that we're working on. Is that okay? So that explains carry, which is the same as borrow, and the sign, which is the same as borrow in this specific case because of the range of values that we're working with. What about the overflow? Has anyone thought about the overflow flag? Just think about when is the overflow flag going to be set? When a sign doesn't make sense, right? When does the sign not make sense after a subtraction? The result of the subtraction has a value that is outside of the range of values that can be represented by a signed 8-bit number. Is that possible? Not in this case. So JOI will work in every single case. It doesn't matter what your student ID is, JOI will always give you 6 times through that no op instruction. So if you answer JOI, it has got to be the right answer. But there might be some other instructions that will also give you 6 times through that no op instruction. Is that analysis okay? How many of you figure out what the program actually did instead of just copy and paste and run it? Sort of? Okay. I like that kind of wavy thing.
Well, like I copy pasted it, and then when I got done, I was looking like, oh, that's what it's doing.
Okay, so to figure out what this program does, my recommendation, if you have time to do it, my recommendation is to log the program counter, register A, register B, register C, register D, and pay attention when the program counter is here and here. Because then you will see how register A and B, they are just incrementing, and one is always just one more than the other. And then when you look at C and D, they are basically the content at the location that register A and B are pointing at. So if you observe that, in the trace, then you will go like, oh, okay. So just from observing the trace, you can start to figure out what the algorithm is doing. We'll talk about how to disassemble programs later. In other words, we'll talk about techniques to kind of reverse the whole process, starting with the assembly code. How do you reverse it back into C code? It's called decompiling this is called decompiling. You start with assembly code and then you're going backwards. Is that okay? Now, since we're talking about this decompiling, so is this particular lab okay? I mean, are there any more questions about this lab? The lab on Monday. If there are no questions about that lab, I am going to go back to one lab before, because there was one question that I really like to kind of touch on. I know most of you know how to answer that one, but it's still kind of interesting to take a look at one more time. And I think it is just this one here. And let me do a preview, and I believe it is the last question of this lab here. So the last question is something like this. I give you a whole bunch of bytes, and then I ask you what is the value of register B when the program hits the halt instruction. So you look at this and go like, it doesn't look like a program to me, but it is, because what are opcodes? If you just look at a byte in RAM, can you tell an opcode apart from actual data that you're storing? There's no way you can differentiate. Because 0, 0 can be a no op in terms of opcode, but it can also be just 0 as a value. So there's no way you can differentiate. So that means when you look at 109, it can be the bit pattern can be anything. It depends on the context. So when you look at 109, you first have to convert this base 10 number into a binary number. Okay, so if I convert this into a binary number, it is 64 plus 32, so that takes up 96, so we got 13 left, so that's a 8, 4, and 1, okay? So we got 1 here, no 2, 1, 4, 1, 8, no 16, 132, 164, and 0, 128. Okay. Well, I mean, I hope, do you guys understand how I came up with all those zeros and ones? Okay. So I can do it probably a little bit faster than you can because I've been doing this for 30 something years. So some of you are not even 30 years old. So that gives you a little bit of context. So when you look at this, you go like, okay, so we know it is representing 109 as a value, but what else can it be representing? Maybe some kind of opcode, right? So when you look at this as an opcode, this is a 6 in hexadecimal, and this is a, let's see, it's a D in hexadecimal. But the most important part is you look at the bit pattern in the opcode table, and you say, is this matching one of the known opcodes that we have talked about in this class? So let's see, is that the, yep, opcode table is right here. So you look at this column and you say, okay, can I find 0, 1, 1, 0 first? Yep, we find 0, 1, 1, 0. Can we find 1, 1, 0, 1? And we can find, in fact, 1, 1, XX, okay? So that means whatever opcode 109 is representing is in this family, because the XX means it can match 0, 0, 0, 1, 1, 0, or 1, 1. So in this case, XX is actually 0, 1, which means I'm using the second register, otherwise known as register B. The mnemonic is LDI. So it's LDI B, comma, something. So now the question is, what are we loading it with? So now we know it's a LDI, a B, and then what is the other thing that we are specifying? What is the immediate operand? So you go back to the question, the immediate operand is really just whatever byte is next to it. So that's an L1. Right there. So this process is called deassembling. Okay? The previous process that I was talking about is called decompiling. So decompiling gets back to a high level programming language. Deassembling is starting with binary code and we end up with mnemonics. Is that okay? So now we took care of the first 2 bytes. The third byte is 117. So we want to figure out what 117 is. So what is 117? I cannot remember. So let's figure out the math. 64 plus 32. That takes care of 96. So we have 21 left. So there's a 16. And then there's a 5. Okay, so plus 4 plus 1. So this one is close to the other one. It is 1, 0, 1, 0, and then we have a 1 here, a 1 here, a 1 here, and then a 0. So when you look up the opcode table, we're looking for something that will match 0, 1, 1, 1, 0, 1, 0, 1. So let's go ahead and look at the opcode table. 0, 1, 1, 1, 0, 1, 0, 1. Ah, that will match, right? So if we use that particular pattern, that means XX is 0, 1, YY is also 0, 1, which basically means the mnemonic is that an LD? Yep. So it's an LD instruction, and the register that we are using in both X and Y are register B. So we are loading B indirect from register B. So those 2 are the instructions. When you go back to the question, the next byte is a 1, which is the halt instruction. So we have a halt instruction here. And then we have the label L1 as a label definition. And then we have a byte L1. And that one is just, it's just what it is. So what this program is really doing is it is first
loading B with the address of L1. Okay? So now B has the address of L1. It is using register B as a pointer. It goes to whatever location B is pointing to. But guess where B is pointing to? L1. And then what is at label L1? It also has L1 as its content. So that's why B ends up with whatever L1 is. So now the question becomes, where is L1? Well, that's a matter of counting. How many bytes, have we encountered before we see the definition of the label L1? That's the question. So this is byte 0 in RAM, byte 1, 2, 3. This is 4. L1 as a label is defined as 4. So that's why register B has a value of 4. Now, with this question, I wasn't expecting you guys to disassemble the program, execute it in your head, and then figure out, register B has a value of 4. I was expecting you guys just to run it, get to the whole instruction, go to the register bank, look up register B, and say, oh, it is 4. Write it down. You're done. But I'm explaining a different process that can get you the answer without the use of the simulator. So is that okay? Cool? All right. So are there any other questions about the previous labs that you want me to go over? Because, if you do have questions, we should use class time to go over those. No particular questions? Yeah. Floating points were not, the floating point questions were not in the previous exam, so they will be recurring in the next exam.
So would it be possible to say that
We could do that. But I want you to be a little bit more specific. Do you have any specific request?
so do you say I put like verbal or ELP?
It will be a general question. It will be asking you, this is the value that I want to represent. What does it look like as a double precision floating point number? But I'm not going to pick I'm not going to give you numbers like in the lab activities. Those are really kind of difficult to convert to values. I'll give you things that are easy to convert, like 6, 0.75, 0.125, 0.375. Those are all really easy numbers to convert because they are natively a magnitude, or not magnitude, a quantity times 2 to the power of something. So by that token, 96 is also really easy because 96 is 16 times 6. So once again, we have a quantity times a power of 2. So anything that is easily expressed like that are fairly easy to convert. Yep. If I give you like 1/3, that would be pretty hard. Well, it will have recurring digits. You just have to figure out the pattern in that case. Okay, all right. Any other questions? No questions? Okay. So if there are no questions, we'll go ahead and start to look into how we convert C code into assembly code. So we'll go with well, I'm thinking about whether I should use a statement form or whether I should use ternary operators. What do you guys want? Statement? Okay. We'll do statement first then. Okay, so here's the function, okay, maximum, and we have x and y as the parameters. So this is a pretty easy function to implement. If you want to use statements, you can say if x is greater than y, then, okay, as much as I hate to do it, we can do it like this, okay, just for simplicity. And then you can have an else. The else is not really needed, but it is usually a good idea to do that. Is that making any sense? Okay, I'm trying to find the maximum of the two parameters and return it as a value. So if x is greater than y, then x is the maximum. Otherwise, y is the maximum. Because we only have two things to choose from. So if one is not the maximum, then the other one has got to be the maximum. So now the question is, how do we implement something like that? So when we implement something like that, I'm not going to talk about subroutines yet, or how to return a value. So we're going to change this code into something that is outside of the context of a subroutine. So we're going to use registers to do all this. So I'm going to say if register A is greater than register B, then register C is register A. In other words, I'm using C to remember who is the larger of the two. So in this case, C equals to B. So I'm just focusing on this code here. Everything is already stored in registers. I'm not using any memory locations to store the data. So the question is, how do we do this? Is that okay? So do you guys remember, flattening code in structure code? Maybe. Did you guys read the module that talks about compiling code? No? Okay. Well, you were expected to. You were expected to read that. So I'm going to use the content of that module. It's not really that difficult. Okay. So the first thing we do is we say, okay, let's negate the condition. And then we say, okay, if the negation of the condition is true, then we go to the else statement. So I'm going to say else label just to be sure, just to emphasize that we're dealing with a label here. So this is the else label, the definition of the else label. If we do not get to the else label, that means A is greater than B is true. So we can now just do the C equals A, and then we go to AND label over here. At the else label, we just perform whatever the else block is specifying, which is C equals B. And then here we have the AND label definition. So when you compare this chunk of code versus this chunk of code, do you think they are equivalent? Yep, go ahead.
You said the other day you flattened code, so you had it all lined up with no indentations.
Yep.
So
Okay, so let's get rid of the indentations here. In the notes, they are indented just to emphasize which block is which block. Yep. But in terms of levels of nesting, they should not have indentations because we actually do not have nesting anymore. Is that making any sense? So in terms of C syntax, there's no nesting anymore. There are no curly braces. But in terms of the logic, there's still that structure, except it doesn't look like that anymore. So are we convinced the top code, which is in normal C code, is the same as the code at the bottom? Yes? Question?
Why didn't you just write it
Because I'm looking for a reason to go to the else label. It's just a mechanical way to do it. Is that okay? So then the next thing we do is we say, okay, can we simplify the condition a little bit? Okay, well, not greater than is the same thing as less than or equal to. Okay, so we have less than or equal to, like so. And then we can look at this and go like, well, according to the assembler, we can check equal to because of the Z flag. We can check less than because of the L flag in this case, because these are signed. But we don't have one that will check less than and equal to at the same time. It's okay. We can have both of those things. So at this point, this code is still in C. In other words, if you don't know whether your program is flattening correctly or not, you can always test your program using the original code, which is this part, and then you can test your program again using this code as a C program. This is still valid C. This is syntactically correct C. And if you did the translation correctly, it still has the same behavior as before. It just looks a lot ugly. Is that okay? So at this point, I cannot simplify this any further, so it's time to actually convert it into assembly code. So to convert this into assembly code, I'll do it this way. So let's, I'm just thinking about how to do this.
Okay, I'll do it. Okay, I'll do it this way. So I'm gonna save the file first, and then use another editor to do this. So we'll save this one as max.ttpasm, which is an extension that I invented to emphasize this is assembly for text toy processor. And then on this side, I will reopen that file, which is max.ttpasm. And the reason why I do this is because I like to use VI. There are tools in VI that I really like to use here. The first one is I can enable line numbers, so that when we talk about the code, we can refer to line numbers instead of that line. No, that one, the one that is 2 lines below that. So this makes it a lot easier. And the other thing I can also do in VI is I can run commands like this. So 1 specifies line 1, $ specifies the last line, S stands for substitution, and then a slash is a delimiter of what we are looking for. A caret is a regular expression symbol that means the beginning of a line. Another slash ends the pattern that I'm looking for and begins the pattern of the replacement. And then what I'm trying to replacing it with is a single slash, which is escaped here, another slash, which is also escaped here, and then another single slash to end the pattern that is the replacement part. And then the G to means if it occurs multiple times, which it does not, replace all of those occurrences, and then press the enter key, and you can see how all lines are now commented. This is just one of the many tricks you can do in VI. If you plan to become a computer science student and become a developer, I really think that VI is a must. Okay, learning how to use VI proficiently will help you in the future. I know we have all kinds of IDEs now, Coblox, Eclipse, all kinds of stuff like that. I still use VI most of the time. Call me old-fashioned.
I prefer old school.
Old school, yep. So we'll do the easy stuff first, okay? C is A. Okay, so which mnemonic should we use? No, not one of the LDs. It's a copy command, so you got the right starting point, but it is not the LD. So let's go to the opcode table and see if we can find something that is going to help us here. Copy register, CPR. Okay, so we can indeed use CPR as an instruction. So the order is still the same. The one that is being changed is on the left-hand side. The one that is providing the value is on the right-hand side. So it is just CPRCA in this case. What about the go-to statement? Jump I. Very good. Okay, so it's JMPI, not just jump. So, and we even preserve the name of the label, so that would work. And then the label definitions are uncommented because they are exactly the same in terms of syntax as in the C program. Okay, it's just the name of the label with a colon, so they can be exactly the same. This one is also easy. It's another CPR instruction. This time we're copying register B to register C. Okay, so the only part that is kind of difficult is line 1. Line 1 is the only one that I have not converted into assembly code because there are 2 steps involved, 2 and a half, almost 3 steps. In C and C++, the act of comparing and specifying what you're looking for is one single step. So when we say A is less than or equal to B, we are both specifying that yes, we want to compare A and B, but we are looking for the relationship of less than or equal to. It's combined into one single operator. In assembly code, we cannot do that. In assembly code, compare is one instruction. Conditional branch is another instruction. So those are 2 different instructions. So that's why the first thing we need to do to implement line 1 is really just a compare. Compare A to B, which is the same thing as A minus B, but do not store the result anywhere. We're just going through the same motion of comparing, of subtracting, but we are setting the flags and remembering all the flags in the flag register. The second line after the compare is going to be a conditional branch instruction. So we're going to do a J blah blah I to label the label else label. So which one should I use? Well, it's less than or equal to, right? So we'll use L first, okay? So that will work in most cases.
In this particular context, it would have worked. The code is fine if we just use at less than. But if you look at the excuse me, original C code, it's also looking for equal to. So if A equals to B, we also want to go to else label. Now, of course, in this program, it doesn't really matter because if A and B are the same, you can copy either one to C and C will still be the maximum. Does that make any sense? But just to be accurate to this original C code, we want to implement exactly the same logic. So that means we have to follow this up with a JCI instruction, because this is basically saying, oh, if the L flag is not set, let's check the Z flag. Because if the Z flag is set, we also want to go to else label. Is that okay? Is that cool? All right. So now we want to test this program. We want to check it out and say, okay, is it correct? So it is time to copy and paste this code into the assembler, extract the RAM file, load the RAM file into the processor RAM component, and then run it. So when you run it, now everything that I'm doing right now is somewhat related to your lab activity tonight. So including the process itself. So I'm going to save it first. And of course, I know you guys are not using VI, so that part is, it's up to you. And I have to use mousepad to open the same file again because VI doesn't have copy and paste, or at least the command line version doesn't do that. So I have Control A, Control C, go back to the spreadsheet, go to the assembler sheet here. And then we go to the source tab, paste, wait a little bit, wait until the progress bar is all done. Make sure there are no errors. And then we go to the RAM file tab, go to File, Download As, CSV, and then we just give it a name. I'll call it Max because that's what it does. Alright, so Max is now saved. We now switch back to Logisim. Right click here. Oh, okay. First thing to do is to reset the whole thing. Control R. Okay, so Control R first. Reset the whole thing. Right click, load image. And we want max.csv. And here's our program loaded. Now, once I reset the whole thing, whoops, it was, oh, I just hit all the windows. That's okay. So we go to the registers because we want to test the code with some specific values. So we go to the registers and go like, what do you guys want to specify? We are supposed to be doing a signed comparison, not an unsigned comparison. Let's do something tricky. Okay, let's do something tricky where we are using the signed interpretation so that, let's say A contains a, which branch do you want to go with? The then branch or the else branch? Yes, I think the else branch is the fun one because we'll see the conditional branch actually happening. So in order to do the conditional branch, A has to be less than or equal to B, but we want signed interpretation or something that works only when it is in signed interpretation. So I'm going to put FF into A, and I'm going to put, let's see, anything would do, 0 would work. We'll make it 0, 1. Okay. So in signed interpretation, what is FF represented? FF is the hexadecimal representation of a bit pattern. But if I want to look at that bit pattern as a signed 8-bit integer, what value is it representing? -1. Very good. Because F in hexadecimal is representing 1111 in binary. So FF is 1111, 1111. So when you look up the number wheel, the pattern that has all the ones is always 1 less than 0 in signed interpretation, which is -1. So that's why FF is representing the value of -1 when it is interpreted as a signed 8-bit number. Is that okay?
is -1 less than 1. So it should branch with that JLI instruction. It's not going to branch with a JCI instruction. Because a JCI instruction, we look at this subtraction, which is FF minus 1, which is 1 minus 0 0 0 0 0 0 0 0 0 1. And it goes like, we don't need to borrow, because we start with 255, you're taking 1 away, there's no need to borrow. So that's why the carry flag is going to be clear, not set in this case. Okay, so now that we have the registers all set up, let's go back to main. Say that one more time. The program itself is using JLI, which is going to branch, but if you use JCI, then it's not going to branch. And that has to do with the signed interpretation versus the unsigned interpretation, which is basically choosing which flag you pay attention to. So that's the most important part of converting from C programming concept to assembly language programming concept is in C and C++ and all normal programming languages, the signed, or whether an integer is signed or not, that information is attached to the type of a variable. In assembly language programming, there's no such thing. Registers do not have any native type. You can look at it as a char, you can look at it as an unsigned AB integer, you can look at it as a signed AB integer, you can look at it just 8 individual bits. There's nothing specific there. Okay? The interpretation comes when you choose what flag you use after a compare. That is the time when you have to pay attention and go like, are we dealing with signed values or are we dealing with unsigned values? It's when you use the conditional branch instructions. Which flag are we paying attention to? Is that okay? So that part is kind of important. You might want to write it down. So now we go to simulate, and then we go to logging. The typical thing I would log is the program counter for sure, because the program counter always tells you where you have been to in the program, so it is particularly important. In this case, I would also log register C, because register C is the one that is going to store the maximum value. So I want to keep an eye on that one just to make sure that it is storing the correct maximum value. So we'll do a change rate X because I want everything to be in base 16. The flags register can be useful too because I want to look at the flags register after the compare and make sure that the L flag is in fact set in this case. So the flags register is, let's see, it should be up here. Yep, there we go. So we're going to add the flags register. This one will keep it in base 2 because otherwise we have to convert it back to base 2 just to figure out which flag we're looking at. So this one will keep it as a base 2 number. Let's see, what else do you think might be important? Register A and B are not important because we already know and they do not change during the execution of the program. So we know A is FF and then B is 0, 1. So that's not important. I don't think there are any important registers to look at this point. Do you guys want to look at anything else? I mean, no? I do not want to change it to base 16 because I want to look at the individual flags because specifically I'm looking for the L flag, which is the most significant bit. And if I represent it as a base 16 number, then I have to convert it back to base 2 to find that bit. So it's like doing nothing. It's doing extra work, actually. So I think these are the ones that I want to utilize to illustrate how this program works. So when this is all done, I'm going to go to File tab and specify a log file. So the log file is going to be named, now this is up to you. I would use something with an extension of TSV, which stands for Tab Separated Value, especially if you use Windows. Because if you use Windows and you want to use a good tool to help you analyze the result of the log, like Excel or LibreOffice or something like that, knowing that this is a tab separated value file helps your spreadsheet program to parse the content correctly into the right columns. Then you can actually use all kinds of tools to analyze. So I recommend the use of TSV and click save. So now we have a file that is associated with a log. Include header line, probably a good idea because otherwise we cannot tell what column is what column. Close window, we are ready to go. There's one more thing to check. Did I put in a halt instruction at the end? I did not. Okay, well, maybe we should include a halt instruction at the end. So let me just look at the original code here. So I want to put a halt instruction here. But I don't want to go through the whole assembling, download process because it's just a lot of work for that one extra byte. So instead of doing that, I can go to Logisim and just say, okay, the last instruction is 0, 1. It's a halt instruction. So you can actually quote unquote hack your program by injecting instructions or opcodes where you think, I think that should be a 0, 1 to turn it into a halt instruction. Because otherwise all the zeros are basically no op instructions. So turning it into a 0, 1 turns it into a halt instruction. Are we good so far? Alright, it's time to run the program. So the idea of using a log is you don't have to single clock through it anymore because single clocking is very time consuming, and if you miss the event that you're looking for, then you have to start the whole process over again, which is no fun. So with all this stuff already set up, the log is already set up, you just type Control K and it will clock at full speed and it's done already. Okay? And we can type Control K one more time to stop the clock because there's really no need to keep running the clock. And then we look into the register bank just to make sure that register C is supposed to be what again? What is the maximum again? Out of FF and 0, 1, which one is the maximum? 0, 1 is the maximum. So we're expecting register C to be 0, 1. So let's double check. Indeed it is 0, 1. Now just because register C has a value of 0, 1 is kind of comfortable, but it's not a real confirmation that your program executed correctly. Because there could be other reasons why register C ends up with a value of 0, 1. So this is a good time to re-examine the log that we have captured just to see, okay, is the log consistent with what we predict this program would do? So before we compare against the log, the first thing we need to do is to look at the program itself and go like, okay, what is the execution path? We know the execution path should be, okay, let me go to this tab here. This is more helpful because it shows you the address right next to it. So we know the execution path is the PC should be 0, 0, so that we perform the compare instruction. Then the PC increments to 0, 1, so that we can execute the JLI instruction. So that is, up to this point, there's no branching involved. The JLI instruction should branch, okay? But the PC should also increment from 0, 1 to 0, 2, just to get the byte that has the value of the else label. So we're expecting the program counter to increment to 0, 2, but it won't increment to 0, 3 because the next cycle is going to load whatever content is at location 0, 2 into the program counter. So that will basically change the program counter to else label. So we should expect the program counter to be 0, 8 after 0, 2. Is that okay? That is when we change register C to become the same as register B. So when the program counter is 0, 8, I take it back. When the program counter is 0, 9, because the decode operation also increments the program counter. So by the time you execute the instruction of the opcode, the program counter is already incremented to the next location. So that means when we see that the register C is changed, we are expecting the program counter to be already incremented to 0, 9. Is that okay? And then when the program counter increments from 0, 9 to A, it will get the halt instruction, which is not in this code because I just injected that into RAM directly. But when we execute the halt instruction, the program counter will actually be 1 byte beyond that, which is 0B. So that is, that's how I can predict the execution of the program prior to looking at the log. Okay, for programs about this size, I recommend that you guys try to do it too. Write the code first, predict what it's going to do, then you check your log to make sure that your prediction or the way you model the behavior of the processor is correct. So this is a big part of how to study for this class. Okay, there's no text per se to study at this point. So studying really involves, writing some code, testing it, making sure that you do understand how each instruction works and how they work together as constructs. Is that okay? All right. Okay. So let me show you another tool that is kind of really helpful. Let me go back to here, and I'm gonna go to new, and get a new spreadsheet. I might have shown you guys already, but it's okay to show again. So I'm creating a new spreadsheet. I'm gonna rename this one. This one you can see also. It's already in the share folder. So I'm gonna rename this one as max log, okay, which is the log of that particular program. So I'm gonna use file, but this time I'm using import instead of download as, which is the reverse of that process. So import allows you to specify to import the content of a file, which can be in Google Drive already or on your local hard drive. It can import the content of that file into a spreadsheet. So I would go for upload because it is actually on my computer, and it is in a temp folder called test.tsv and this max.tsv, which is this file. Click open. So it will first upload, and it will ask you about these options. Import location is kind of entirely up to you. Since this spreadsheet is completely empty at this point, I'm just going to say replace current sheet, okay, because I don't have anything else to do with this particular spreadsheet. Separated type, you can have it detect automatically, which probably will work, but since I already know this is tab separated, might as well just select tab. And convert text to numbers and dates, I would say no. The reason why you want to say no to this one is because if you try to convert text to numbers and dates, then it will do something really funky with hexadecimal numbers. If a hexadecimal number does not have A, B, C, D, E, F, then you'll go like, oh, this looks like a base 10 number, let me convert it for you. If it has A, B, C, D, E, F, then you go like, oh, this doesn't look like a base 10 number, I'm not going to do any conversion. So your numbers will start to align, some will align to the left, some will align to the right, and all the leading zeros will disappear. It just doesn't look right. Okay, so I would just select no or convert text to numbers and values. And then we click import data, and here we have the trace. So we have the PC going from 0 to 1 to 2 and then to 8 to 9 and then to A. Okay, when is the register changing? The register changes, or register C changes when we get to location 09, and it changed to 01. What about the flags register? The flags register is updated at this point when the program counter is 01, because the compare instruction is at location 00. And the most significant bit of the flags register is the L flag. That's the one all the way to the left. So we have to have the L flag set. So all of these things are confirming what I said earlier by looking at the program and executing the program just in my head. Yes? The other ones, if I remember correctly, I think the least significant bit is the carry flag. So this is carry, this is 0, this is sign, this is overflow, and this is the L flag. But you can also confirm that by looking into the processor's, what is that called? ALU. So when you look into the ALU module and you scroll all the way down to flags out, how we use this merger to merge these individual pins also helps to explain which one is which one. So you can see bit 0 is the carry, bit 1 is the 0 flag, bit 2 is the sign flag, bit 3 is the overflow, and then bit 4 is the exclusive OR between the sign and the overflow, which we otherwise know as the L flag. So there are multiple ways to kind of confirm that. But I would go to the source. That's the whole reason why this whole thing is open, so that you can actually look at the entire design and confirm, how everything works. Is that okay? Has anyone printed out or at least have a copy of this in PDF sitting somewhere on the drive or in your binder folder? You might want to start to do that, because you might want to kind of refer to the design itself and start to annotate as you start to understand more about the design. I would make copies. It's like, for this instruction, these paths are established. For this instruction, these paths are established. So this way, it is visually telling you, reminding yourself for each instruction what type of multiplexer is connecting which wire to which wire and which component is active. Is that okay? I know it sounds like make your own textbook kind of project, right? But no two persons would learn the same way. So the way you learn is up to how you want to document the process of it. I will try to give you an example of what I meant earlier. Do you guys kind of know what I was talking about, or have absolutely no idea what I'm talking
Talking about processors.
about?
Talking about processors.
Yes, but the but the idea is you basically generate a PDF of the processor, just completely static and not doing anything. Okay, let's see, what time is it? 8 o'clock. We got 20 minutes. Yeah, I got enough time to do this. So I'll illustrate what I mean by that. So let me go to File, and then we go to Print, and I'm going to print it to a PDF file. So no print surface found, or doesn't like that. Okay, can we export image to, well, PNG is fine, okay. Give it a name. Okay, we go to the temp folder again. This is processor.png. Now it's exported. Now, depending on what kind of tool you have, on your PC, it's up to you of how you want to do this. There's a really cool program called Inkscape that I find to be useful in many applications, including what I'm about to do here. So I'm going to start up Inkscape. And we'll go ahead and get the document in, which is import. So we'll specify processor.png, and we'll do embed, which means we are not only linking to that file, just in case we move that file to somewhere else. This SVG file is going to be standalone and can exist on its own. So what you do is you basically just put this onto a empty document, like so, and center everything. And you want to save this one first. Okay, so I'm going to save this one, and I'll save it as, okay, we'll go to the cisp310 folder, and we'll call this processor template, because I'm going to make copies of this. Okay, for every instruction I'm going to make a specific version of this. So now it's time to zoom in. And then what we are going to do is to say, okay, let's just talk about the Cpr instruction. Okay, so we want to find out, how the Cpr instruction works. So we want to find out what components are active, what pathways, how the multiplexers and demultiplexers are making connections. Okay, so you have to first run it in the simulator once, just to figure out, how the multiplexers are going to work. But after that, you would know that the register bank is going to be active. So now is a good time to highlight it if you want to. So I'm going to use a tool to highlight it, this one, and then we can just do something like that. Obviously, that's not going to be very helpful. So we'll go to fill and strokes. My computer's just being slow. Yeah. Yep. So when we go to fill, we can say you can have a transparency, so you can change your um, how opaque it is to a smaller value. Oh, okay. I'm changing the rest of the picture, not the one that I want to change. Okay, let's undo that. And you can also use layers too. By the way, you can also use separate layers. Let me show you how to do that. So you can go to layer, you can add a layer, and we'll call this new layer, highlight. Okay, and then you can go to a dialog box to look at the layers. Okay, so which one? Right there. Okay, so we can see that we have a highlight layer and a layer. You can change the ordering to see which one is on the top. So by default, highlight is on top, and we want it to be the opposite. So we select that one and say, okay, we lower highlight to a lower level. And because it is selected, so that means whatever I'm doing is I'm doing at the highlight layer, which is below the image itself. So at this point, I can now do some highlighting, okay, which is the same thing as what we did earlier. Unfortunately, that didn't work because it is not transparent. The pixels are actually white in color, so whatever is behind it doesn't show. Is that making any sense? So for this to work better, you have to make the processor PNG file, what appears to be white, you want it to be transparent so that you can actually see behind it. Is that making any sense? Alright, so we're going to bring another tool in to do this. So we go to the GIMP, and we'll have to redo the other one, but we'll fix that later. So the first thing is to introduce transparency into the original schematic. Now, of course, for those of you who are more tactile and just say, I can do this with a piece of paper and a highlighter, do it that way, okay? So this is not the only way to do it. It's just that, if you want to do it this way, I personally would prefer to do stuff like that. So we're going to open it in the temp folder, processor.png. This is another one that I have saved, but it'll be fine. Okay, so we open this one. Okay, and then what we do is we have to go to we want to introduce transparency, so we go to, I think it's layers, and we want to go to transparency, add alpha channel. So now we have alpha channel, and then we want to select by color using this tool, and then you just click somewhere that is white. So it will automatically select all the pixels that are of white color, and then we press the delete key to get rid of all the pixels or get rid of all the colors white, and so now it's transparent. And now we can re-export the file. So we say overwrite processor.png, and hopefully this is the right PNG. So we're going to click Save As to make sure, okay, it is the right one. It is in the temp folder. Okay, so our work is done here in the GIMP. And we'll quit this one so that we don't have too many things on the screen at the same time. And then we go back here, and then we go back to layer 1, select the bitmap itself, delete it, and you can see how in the back it is actually the highlight is in the back, but we couldn't see earlier. Then we re-import the PNG, but this time it has transparency, which is cool. Do embed, and then we want to zoom out just to fix its location. Oops. Okay, when it's transparent, it becomes much more difficult to grab, because you have to grab a place that is either something like this or some location that is not transparent. Okay, now we in business, because now we can go back to the portion that we want to look at, which is about this portion, and then we change to highlight, and then we can now start to actually highlight stuff. See how the color blob is actually behind the frame? So this is where you can actually do some highlighting. And you can use a wheel to select what color you want to use to highlight the portion that is active. And you can also use the hand tool or the pencil tool like this one. And when you use a pencil tool, you can also change the color. And then you can start to say, okay, what connections are active at this point? So with CPR, this is active. And it goes through this multiplexer to go back into the input. So I'm just tracking which one we should be looking at. Is it this one or? I'm looking for a path to get back to the input of the register bank. This one goes to okay, so we are looking at this one here. So you basically highlight, use a pencil tool, trace this thing here. And it goes through this particular multiplexer all the way back to the input. Something like that, okay? You know, I know this is squiggly and it doesn't show very well because I put black color. You can always change the color. But the idea is make lots of copies of the processor architecture itself and then use either pencil, paper, highlighter, or electronically. Highlight the components, highlight the paths, highlight how the multiplexers are working, and then you have a visual way to remind yourself, oh, the LDI instruction is actually configuring the processor like this when it executes. The CPR instruction configures the processor like this when it executes. The JMPI instruction is like this when it executes, and so on. That is how you can study for this class, is to have one processor architecture picture per instruction. So we are talking about how many instructions again? 30? About 30, but some of those are families of instructions. So most of the things that go through the ALU, you can kind of combine most of those into one single picture. The JXI instructions, the conditional branch instructions, the entire family is about the same, so you can combine those into one single picture. So we are not really talking about 30 individual pictures. We're talking about maybe 20-ish, kind of picture. Do you want to document the no-op instruction using a picture? No. What about the halt instruction? No. So there are some instructions that you do not need to update. You don't need a picture to visualize what's going to happen when you execute those instructions. So we are really only talking about 20 pages, which is not a whole lot. And it is some exercise that you can do on your own, okay? You can do on paper, you can do it electronically, and some of you have, fancy, tablet computers, and you can do it on the tablet. Is that making any sense? So that is one way to study. So I'm giving you guys ideas to quote-unquote study for this class and prepare for the exam at the same time, because it is open book, open notes. Guess what you can do with those 20 pages that you just created? Bring with you to exam 2, because you can count on it that you will need them. It will be the practice exam right after you come back from this framework, and then the week after that we'll have the actual exam. Sorry? Did I say anything about 440? For those of you who were in 440?
I think it's Wednesday.
So 440 is Wednesday, so let's make 310 Monday then. So we can stagger the exams. Unless you guys want to do the same exam.
4:30 though.
Huh?
This is the program.
You should have taken semester, huh? So we'll do 440 on Wednesday and 310 on Monday.
Wait, so the practice exam on the Monday or the real exam?
The practice exam
Okay.
on the Monday.
Exam on 440 is on Monday.
Oh, is
The
that
real
on Monday?
exam's on Wednesday.
Sorry?
The real exam's on Wednesday.
No, the real exam is always 1 week from the practice exam.
So our practice
Okay.
exam in this class is on Monday, correct?
Yes, that's the proposed date, is to have the practice exam on the Monday right after the break,
Okay.
which means the actual exam is 1 week after that. And then for 440, it is going to be the Wednesday. So I can stagger those two exams. Is that agreeable? Okay, cool. Let me check. I'm not very good with time or dates. So the Monday when we come back is the 9th. So for this class, the 9th is the practice exam. Huh? The 2nd? Okay. So the 2nd is the practice exam, and then the 9th is the actual exam. Would that work? Okay, all right. And everything is being recorded, so if you forget, just get to the last 5 minutes or so of the lecture, and it's all there. Any other questions? Revisiting the labs can be helpful, to prepare you for the exam. So you're not going to be just looking at the question because you have gone through those questions already. So what you need to think about is what variants, can you come up with those questions? How can you change those questions a little bit and ask something that is different? Is that okay? Did you guys learn how to model your teacher's way of thinking, and then you can predict what kind of questions will be in an exam? Okay, so sometimes that works. With me, maybe not.
Probably not.
Or you know what kind of pattern you like.
Hmm?
You like proofs, you like makes it harder. What type of questions you like to do?
I usually ask questions that requires critical thinking and problem solving. And that's why it's open book on the notes, because I don't think your brain really should be wasting neurons to remember things, but you should be using your neurons to understand the material to the point where you can apply it. So that's kind of my way of thinking for that sort of thing.
Yeah, I should like back the other day to this classes we taught on YouTube that I watched practice exam lecture. So yeah, that's one of the
Could
just
you-
going over the ones that's on
On the drive?
yeah, on the drive.
Okay, you can do that.
I was just
Yep. Yeah, so I think I'm going to refrain from questions about making new instructions, but I still want you guys to understand, still want to test whether you understand how the microcode works in the context of the processor. So I'm going to have to kind of change the way I ask for some of those questions. All right. 16. So getting back to the main topic of today, are there any questions about this particular program? This program is okay? Looks okay to you? All right. So I can give you a preview, since we have a few minutes, of your lab, and then give you some pointers, because this way I don't have to give those pointers during the lab time as much. All right, so let's switch to the lab for tonight. So go to modules. The lab is already listed in the module, but the start time is not there yet. So your lab is called absolute value. So when you look at it or when you open it, it will be in different type of questions. So I'm not going to talk about oh, this is the first question. So your code, your lab involves converting something like this into assembly code. And that's why I asked you if you want to use tables or you want to use a ternary operator. But the other questions will guide you through the process. Okay, so it's not like you really have to figure this out, because the other questions will guide you through the process. but it's about the same thing as what as what I did in today's lecture. You're given a piece of code, it's a conditional statement, you have to translate that into assembly code. The difference is, this one is a little bit more complex because you have to find the arithmetic negation of a particular register. So you have to kind of remember what we talked about with those particular topics. How do you find the arithmetic negation of a signed number? You have to go all the way back to the module that talks about it, but there's one module that talks about it. Okay, do you guys remember which module? Or where to find that module?
Choose complement.
Choose complement, and where is that?
Numbers, spaces, and values.
I think that is the case. There might be a module just for signed interpretations, so let me look for that. Signed value representation, I think that is the one. So you might need to refer to this one if you have forgotten. So when you go to this one, this is before I put an index at the beginning, so we kind of have to search through it. So we are looking for a complement, and there we go. So we have two's complement, and this part explains what is two's complement. Two's complement is one's complement plus one. One's complement is basically a negation, a bitwise negation, or otherwise known as a bitwise NOT. So it's bitwise NOT plus one. Okay, so knowing that you need to do a bitwise NOT and then a plus one, so now the question is, do we have mnemonics or opcos or instructions that can do those things? So I will give you a quick clue here. The answer is yes. We do have bitwise NOT. We do have add one as a single instruction. So that means the actual two's complement operation involves two instructions. You just have to know which two. Okay? So getting back to the homework, the lab activity for tonight. So the other question is, how do we know something is less than 0 or not? Okay, in other words, we're focusing on this comparison, because if x is less than 0, then we have to do some negation. If x is not less than 0, we don't have a single thing to do, because the objective of your code is to store the absolute value back into the same register. So if the register already has a value that is not negative, you just leave it alone and go like, I'm done, alt, I'm done. Excuse me. You can just say, press your times. N, and then n plus 1, and then n plus 2, right? Okay, so how do you know whether a number is negative or not? So for this, you have to go back to signed number representation. Okay? And then the question is, there are many ways to check that, okay, by the way. You can do an actual comparison and then look for a flag. That's kind of the long way to do it, but if that's the only way you can come up with, that's okay. It's not a problem. I'm not looking for the optimal solution in the lab. But there's another way to check which flag, whether the signed flag of a particular register is set using a very awkward instruction. Okay, that is already in the instruction set, but you don't use it very often. The questions will guide you through the whole process. Okay, so that's the whole idea is the first 3 questions, the first 4 questions or so, will kind of guide you through, and look at all these individual pieces and suggest, what opcode or what instruction you might want to use to check for the sign flag and stuff like that. And then the last question is for you to actually figure out the actual entire program. And then when you're done, copy and paste it into the HTML editor, turn it in. That's the whole lab activity for tonight. So let me skip to the last question. Because I know some of you can get all of this done in a very short amount of time. So for those of you who can get it done in a very short amount of time, your challenge is going to be this part. Text version of this program has 7 lines of code, including label definitions and all the instructions that we need in this one. So if you are done and your code has like 9 or 10 lines, you can try to spend some extra time to think about, okay, can I make it shorter? Turn in the one that works first. Okay? Sorry?
Extra credit?
No, not extra credit. Not in that sense.
But
Okay.
it's a challenge.
It is a challenge, and if you take on the challenge, you are basically studying. In other words, if you like challenges, then you're studying for fun. There is such a thing, studying and fun at the same time. When I was a student at San Francisco State University in the computer science program, it was fun. I don't know. People call me odd, strange. But I was really having fun. I go to school every single day and wonder, what am I going to learn today? From 8 a.m. to about 2 p.m.